Okay, thanks for coming to the Experimental Mathematics Seminar at Rutgers University. Today's speaker is Dr. John Lenchner from IBM, who will talk about thinking the foundations of mathematics from a finitistic point of view and the practical consequences. John is a soulmate, and I'm looking forward to hearing what he has to say. Thank you. Okay. As usual, if you have questions, please unmute yourself for a second, ask the question, and then you can mute yourself back. Thank you.
Yes. So, okay. Thanks very much, Doron. And I would appreciate any questions just as you have them. I've minimized the picture of everyone so I could see my own slides, but I presume you can just speak up and that would be great. And also I didn't quite know who I was presenting to, whether it was undergraduates or graduate students or who. So it's, I try to make the material accessible to anyone. So the title is Rethinking the Foundations of Mathematics from a Finitistic Point of View and the Practical Consequences. And yeah, again, my name is John Lenchner. I'm from the IBM T.J. Watson Research Center in Yorktown Heights, New York. Oops. Okay, so first, before we get to the finite, on the infinite in mathematics. So much of mathematics relies upon either the existence of objects that contain an infinite number of elements, like the natural numbers, the real numbers, and so on, or our ability in theory to compute with an arbitrary level of precision, or our ability in theory to compute for an arbitrarily large number of time steps. And this talk is actually an inquiry into whether there's any way to assign meaning to the notions of existence or in theory in these different cases. Okay, so let's for the moment just take a physical realist's perspective on this kind of question. So from the Heisenberg uncertainty principle, making an arbitrarily precise measurement is impossible. The moment we pin down an object in space, we lose all ability to measure its momentum and hence its velocity. However, even without the uncertainty principle, making a completely precise measurement, say of a spatial coordinate, is not possible, since it would take an infinitely long time. We don't have infinitely precise measuring glasses, so we have to focus in on one resolution, get that measurement, focus in a bit more precisely, get that measurement, and so on. And moreover, it would require an infinite amount of space to record the result. Okay, further, what could it possibly mean for a physical object to occupy space up to some measurement k, but not for any k minus epsilon, for arbitrarily small positive epsilon? Okay, so let's just do a little thought experiment. Suppose we had a hypothetical cell with a cell membrane at K and cytoplasm. Okay, this is just a thought experiment, cytoplasm that extends up to but not including K. There's then no space between the cytoplasm and the cell membrane. Are they separate or they're not separate? If you're like me, the more you think about such a thing, the more it hurts your head. I mean, I love the point set topology and the idea of open sets and closed sets, but this concept can't possibly apply to real objects, real things. And so one's left to wonder, are real numbers describing these quantities just a form of mathematical sophistry? Okay, by now you may agree that there's no such thing as a completed infinite object, like a real number. But could it be that there's actually a largest natural number? Okay, so given a finite amount of space, it's not possible to talk in any rigorous way about arbitrarily large numbers. We only have so many bits at our disposal. Storage takes space, be it on a computer, on a written page, or in our heads. These bits can be arranged in only so many ways. There's therefore a largest expressible natural number. Okay, so if n is the largest, what about n plus 1? Okay, you're not allowed to speak about such things. Okay, so it's a fair question to ask if numbers beyond this largest expressible number exist at all. If these numbers are inexpressible, what have we just been talking about? Okay, so let's leave this little expressibility conundrum hanging in the air for the time being. In fact, we don't have a complete solution to it. Okay, with this conundrum in the back of our minds, let's make a couple of additional observations. Okay, mathematics requires the notion of time and space to be intelligible. And this is an argument that was actually first made by the intuitionist Brouwer. So real numbers are expressed as sequences of digits in some decimal expansion that can be understood with respect to time. When we say 1/3 equals 0.333 ... to understand the ... we need to say and so on, referring to the fact that this process could continue in time. We cannot make this notion meaningful without referring to time and space. Real numbers are therefore the expression of a process that somehow generates the digits, either through a measurement or a calculation. Analogously, a theorem requires one to hold the premises in one's mind and then the conclusion, and to come to the realization that from one, the other inevitably follows. In this sense, a theorem is the summary of an activity. The theorem can be expressed using formal language or formal notation. In both cases, the theorem is materialized as bits somewhere, perhaps just in our heads, but nonetheless, it is inescapably bits encoded in time and space and doesn't exist otherwise. And a proof is just a sequence of steps, one following from the next. The following of these steps does not make sense out of time. I mean, they're meaningless if we consider them all at once. I mean, the proof proceeds, the second step proceeds from the first step, the third from the first and second. It doesn't make sense to consider these all without sequence. And here you see a picture of Brouwer, the originator of these thoughts, actually, at the International Congress of Mathematicians. I think it was in 1936. Oh, and I should say, just I know that Jerome likes some of the history. He had a very famous fight with Hilbert around this time, and he was on the board. Hilbert was the chair of the mathematician Annalen, a very famous German mathematical journal, and he was on the editorial board, and ultimately he was their fight forced him to step down. Okay, so I'd like to argue that mathematics and physics are therefore inextricably linked. The Platonic realist conception of mathematics is really a fantasy fed by a psychological sense of what math should be. In other words, the discovery of something eternal, especially with regard to notions of infinity and real numbers and so on. This realization is somewhat analogous to the realization by physicists that time and space are irrevocably bound up and potentially just as important, throwing the foundations of mathematics from Cantor onwards into a little bit of jeopardy. Okay, so this material that I'm going to go over, I'm sure is very elementary to everyone, but nonetheless, I think the historical perspective is useful and perhaps new to some people. So Cantor was a Russian-born German mathematician, lived from 1845 to 1918. And although he famously used the Hebrew Aleph and even Beth to denote some of the first few infinite cardinals, he was actually a devout Lutheran. And he was the originator of the idea of different cardinalities for different size, the idea of different size infinite sets. And he faced stiff opposition to his ideas from many of his contemporaries, including Kronecker, Poincaré, Weil, the aforementioned Brouwer, as well as the famous British philosopher Wittgenstein. And the attacks by Kronecker were famously scathing. Kronecker called Cantor a scientific charlatan and a corrupter of the youth. However, he was vigorously defended by Hilbert, and Hilbert was the strong man of mathematics in those days. So his support carried a lot of weight, and of course, Cantor's very famous to this day. And Cantor famously came up with his diagonalization argument, which led to the realization that infinite sets could have different cardinalities, showing that the real numbers were more numerous than the natural numbers. And he said, well, suppose we could enumerate all real numbers in the interval 0, 1 by their binary decimal expansions. Suppose the numbers here listed are S1 through Sk to go so on to infinity. Then we take the ith digit from the ith number listed and flip that digit to get the ith digit of our new number, and that number can't possibly be on the list. And so therefore, we haven't succeeded, in fact, in enumerating all the reals in the interval 0, 1. And the same argument, much more succinctly, can be used to show that the power set of any set is always larger in cardinality than the set itself. And so suppose f is this function that's supposedly surjective from S to its power set, and consider the set T of elements of S which are not contained in their image under F. And now suppose that T is actually in the image of F. So this is the set, just like the element that I showed on the last page. And we've rigged it so that it can't possibly be in the image of F. Why is that so? Okay, suppose that S is actually, consider the element S that T is supposedly the image of. If S is in T, then by the definition of T, S is not an element of F of S. And so S is not an element of T, which is a contradiction. We supposed first that S is an element of T and have now concluded that S is not an element of T. And then on the other hand, suppose that S is not an element of T. Okay, then because we're supposing that T equals F of S, that means that S is not an element of F of S. And so by the definition of T, S is in T, again, a contradiction. And so T can't be the image of any S, and so therefore there has to be an element of F not in this supposedly surjective map. Okay, so if S is infinite, the formula seems to be somehow not infinite. It's just a very terse expression of why F is not surjective, but in fact it really disguises an infinite amount of work in one stroke. So it's deceptive in its simplicity. Okay, so actually this, I think I said already, the diagonalization argument that I've just outlined was produced by Cantor in 1891. Russell basically used the same idea in 1901 to show that there can't be a set of all sets. And he considered the set of all normal sets, or the set of sets which are not elements of themselves, and asked if such a set could be an element of itself. And by the same sort of argument, you see that it can't either be an element of itself or not an element of itself. So therefore, the set itself can't be a set, for whatever that might mean. And this thrusts the then standard informal use of set theory into turmoil. And the important historical perspective is that this came 1 year after Hilbert's famous address at the 1900 International Congress of Mathematicians in Paris, in which he enumerated his famous 23 problems. Actually, not so well known is that only 10 were mentioned in this official address. The other 13 came in the notes following the address. And in the address, Hilbert famously proclaimed, "Take any definite unsolved problem, such as the question as to the irrationality of the Euler-Mascheroni constant, or the existence of an infinite number of prime numbers of the form 2n plus 1. Actually, isn't this 2n? I think this should be 2n minus 1, right? Aren't these numbers n primes? I'm not a number theorist, but I think that's the case. Anyway, however unapproachable these problems may seem to us, and however helpless we stand before them, we have nevertheless the firm conviction.
Either way,
it's either way? Oh, okay. The firm conviction that their solution must follow by a finite number of purely logical processes. This conviction of the solvability of every mathematical problem is a powerful incentive to the worker. We hear within us the perpetual call. There is the problem. Seek its solution. You can find it by pure reason, for in mathematics there is no ignorabimus." Okay, so by the word ignorabimus, Hilbert was making implicit reference to the Latin phrase ignoramus et ignorabimus, meaning we do not know and will not know. This is a phrase popularized by the 19th century German physiologist Émile de Bois-Reymond, and it suggests that scientific knowledge is inherently limited. Hilbert, however, famously rejected this notion and believed that all mathematical facts could be discovered by formal means. And the famous continuum hypothesis, which was the first of Hilbert's list of problems, asked whether Aleph 1 was equal to 2 to the Aleph 0. In other words, whether there's a cardinal number strictly between that of the natural numbers, Aleph 0, and that of the reals, 2 to the Aleph 0. Equivalently, is there a subset of reals that can neither be put into one-to-one correspondence with the natural numbers nor with the real numbers? After Russell's discovery, it was not clear whether this was still even a meaningful question. So Hilbert obviously had a vested interest in figuring out a way to make this very first problem meaningful. And so what happened was the axiomatic set theory came to the rescue. In order to rescue the foundations of mathematics, various set theories were proposed, with the currently standard Zermelo-Fraenkel set theory with choice little by little taking hold. But a lot of argument about what the proper set theory should be. And in fact, although these axioms are accepted by practicing mathematicians, and in fact, I'm sure that virtually all of them are not even known to the practical most mathematicians, with the exception of the axiom of choice, they're not self-evident. And let me give you some examples. Okay, so the first one, the axiom of regularity, it's basically an end run around Russell's paradox. It says that every non-empty set contains an element that has an empty intersection with itself. Okay, I won't go through the logical description there, and it avoids having a set of all sets in this strange way. Okay, so we consider a set A. Okay, so by another axiom of set theory called, I think it's called the axiom of pairing, you can then form the set containing just A. And now this set containing just A, by the axiom, must have an empty intersection with A, its only element. And therefore, A cannot have itself as a member. So a very peculiar way of stating an axiom which is not entirely obvious, but to get around Russell's paradox. Okay, then there's this also bizarre way of stating that there is an infinite set. Okay, there's actually no really direct way of doing this in the first order theory of set theory, GFC, but get around this by this funny axiom that says there exists an I, in other words, just a mnemonic for the infinite set, and the null set is contained in I, and for every X in I, X union the set containing X is in I. So therefore, from the null set, we get the set containing the null set is in I, and the set containing the null set, so on. And so we get this by observation an infinite set as part of our collection of bona fide sets. And of course, there's the also not completely obvious axiom of choice. And frankly, of all these axioms, this may be the most obvious for whatever we mean by obvious. Anyway, it says that given any collection of non-empty sets, one can form a new set by picking one element from each set. Okay, and from here, von Neumann came up with the idea of creating numbers, and in fact, developing all of mathematics just from sets. So as we learn in many, the first pages of some like real analysis textbooks, at least in my day, antique by comment now, maybe analysis books don't no longer do this, but in my day they did. They developed the real numbers from sets, and so you learn that 0 is the null, can be thought of as the null set. 1 can be thought of as the set containing 0, in other words, just the null set. 2 is the set containing 0 and 1, so the null set and the set containing the null set, and so on. And you construct the natural numbers, then you can construct the integers, the rationals, and then using Dedekind cuts or whatever method, the reals, and so on. And even if you push it to the infinite von Neumann ordinals. Okay, but don't we have this backwards? Isn't a number a more fundamental notion than a set? Okay, if we insist on thinking about numbers as sets, we're tempted to treat the number 3, say, as just the equivalence class of all 3 element sets. But actually, the existence of such a set can easily be seen to run into a simple variant of Russell's paradox. And I leave that as a little exercise for you. So for the non-believers, and maybe Jerome and I are the only ones, but in any event, the part of this is to convert some of the non-converted. Instead of building all of mathematics axiomatically from first order set theory, why not approach mathematics non-axiomatically based on the concept of a bit? We already have a wonderful model of this sort of mathematics, the mathematics we can investigate and record using a digital computer. We can even do set theory if we so choose on such a device. If you've programmed in Python or Java, they both have perfectly wonderful set classes. And of course, all of ZFC, you can prove anything you want, or just the assumptions of ZFC are laid bare when you do mathematics this way. Okay, so with that, let's go back to our conundrum and the limits of expressibility. Okay, given a formal language L and a given number of bits n, what can we say about the largest natural number n star expressible in this language, which I'm going to denote L of n, and the smallest natural number I star not expressible in L of n? Note that in general, I star is much smaller than n star, since although we'll be able to express very large numbers in this language L of n, we'll not be able to express very many of these very large numbers.
I'm sorry, what's L of n?
Okay, so L, so if given a formal language L is the restriction of L used to just n-bit expressions that can just be formulated using n, at most n bits.
Thanks.
Okay. Okay, so before I get into the details of these languages, I'm not going to.
Is it possible for you to just go back for like 2 more seconds on this? I just am trying to parse I versus N. I star versus N star.
Sure. So L is the largest number expressible in L of n. I star is the smallest natural number not expressible in L of n.
Okay, thanks. I got it now.
Okay, so there's
question.
Yeah, but you think about this isn't exactly how it's going to work, but think about doing a big tower of exponents, right? So if you do this huge tower of exponents, you're going to get a very large with your n bits. You're going to have a very, very large largest expressible number, but there'll be many, many smaller numbers than that are not expressible in those n bits. Right.
But it could happen that n star is less than I star, right?
Oh, not possible. Okay, but that would mean that only if you have a very, very incredibly weak language. I mean, it might be you'd have to create some just totally impoverished language that couldn't do virtually any arithmetic or have very few constants. I mean, I think it would have to. Yeah, I mean, even if it could do multiple, let's say your language just consisted of 0, 1, addition, and multiplication. Okay, then you could express 1 plus 1, and then you could express powers of 2, right? And you could, with n bits, you could express, high powers of 2, but you wouldn't be able to express, with that many bits, say 50 less or 7 less than that, because you'd be consuming all your bits just to express that high tower of 2 or 3 or 4, whatever the most efficient way to do that is. Okay, we may see that. We'll see that relatively soon.
So is there like a notion of a good language in which we would want one to be expressed? So like my I star is not enough.
We've started, I'll get to this in a little while, but we've started studying some simple languages and their expressibility properties. And you want to start out with very, very trivial languages, almost not quite as trivial as the one I just described, but close, and see what the limits of expressibility are there, where it's very tractable. It gets somewhat very difficult very fast to understand these limits. But I think intuitively you should see that I star is considerably smaller than n star, right? Because in n star, we're going to reach extremely high. If you know about Graham's number, we'll be able to reach Graham's number, but we're not going to be able to reach, too many numbers much smaller than Graham's number in those bits, right?
Okay.
I hope that's clear enough, but we'll go on. Okay, so there's work related to this, and let me just go over some of that. So in finite model theory, you have Fagin's theorem, which famously says that a problem pi is in the complexity class NP if and only if it can be expressed in existential second order logic, also known as ESO. Okay, so yeah, this is not really the Ron Fagin from this theorem, but I'm actually working with him, and so we sometimes show this funny. Hopefully you've seen the movie Oliver Twist. The bad guy is Fagin. This is Oliver, but actually Ron looks like this, not that. And so what is existential second order logic? Well, we're talking about finite model theory, so it's the model theory of finite structures. And so for concreteness, let's confine our attention to graphs. Somehow this is going by on its own without me clicking. Anyway, okay, so the language of graph theory is the language consisting of one relation symbol, the two-place relation symbol E. Somehow I've got onto automatic mode. And the universe of elements of graph theory is the set of vertices in a potential graph. And E is the edge relationship between the two vertices. Okay, so first order logic is propositional logic, the logic with the usual logical connectives, plus a relation or predicate symbols, together with universal and existential quantifiers that can range over elements of the universe. Okay, so in graph theory over the vertices. So here's an example from graph theory. It says that for all vertices x and y, there's an edge from x to y if and only if there's an edge from y to x, which means that the graph is undirected. Okay, what is second order logic? So it's first order logic, but with quantifiers that can now range over subsets of the universe and relations defined over the universe. Okay, so before in first order logic, we could just range over vertices. Here we can range over subsets of vertices or relations defined on, so the edge relation or other relations like color relations, what have you. And then this special class singled out, sorry about that, singled out by Ron's theorem is existential second order logic, or ESO. And these are formulas of the form, there exists capital X1 through capital X and phi, where the initial there exists X1 through Xn quantify over sets or relations, and there are no other second order quantifiers. Okay, so there are no universal quantifiers. And there's also no quantification in between this these existential quantifiers.
Hey, quick question. Are you allowed to do universal quantification over the vertices, but just not over like colorings or whatever?
So in the phi can contain universal quantification over the vertices. It can't contain any kind of quantification over the subsets or over the edge relations. Yeah, so you'll see that in a second. Okay, and we, by convention, use capital letters to denote the second order variables. In other words, those ranging over sets or relations, and lower order letters to denote the first order variables. Okay, so here's an example of three colorability, famous problem in NP. In fact, it's NP complete. And the way you say this, or one way to say this in existential second order logic is there exists three colors, which I'm using RGB to denote red, green, and blue. Somehow this is on automatic mode. I don't know how to get out of it. Okay, this could be distracting. Okay, so there exists three colors, R, G, and B. And for all vertices, either the vertex gets colored red, not green and blue, or green, not red and blue, or blue, not red and green. And then for all vertices X and Y, crap. Okay. How should I get out of this problem? Okay, anyway, if there's an edge between X and Y, then they both don't get the same color. And Ron's observation is that the form of this logical expression, it's an ESO expression, is not accidental. The existential second order quantifiers correspond to the guessing stage of the NP algorithm, while the remaining first order part corresponds to the polynomial time verification stage. Okay. Okay, so just like NP is equal to ESO, co-NP, if you know about that complexity class, corresponds to the complementary so-called descriptive complexity class universal SO. In other words, replace all the existential quantifiers that I had up front with universals. And now if NP is not equal to co-NP, then it's easy to show that P is not equal to NP. So one way to prove that P is not equal to NP is to show that there are problems expressible in ESO that are not expressible in universal SO. So some progress has been made in this program. An important subclass of NP called monadic NP has been separated from monadic co-NP. However, this turns out not to prove the big kahuna. In other words, separating monadic NP from monadic co-NP does not imply that NP can be separated from co-NP. And so there's still the big guy is out there, proving that P is not equal to NP, or the slightly, perhaps more general NP not equal to co-NP.
Okay. Is the proof difficult or it's relatively easy?
You mean the proof that you can separate monadic NP from monadic co-NP? It's not too difficult, actually. So the proof the example is what's called ST connectivity. So you have a graph, and you want to state whether you can get from S to T in monadic NP. And it turns out that that is not in monadic NP. Okay, but you can let me see, how does it work? Yeah, the proof that that's not in monadic NP follows from a game argument. So that one of the tools to show that things are not expressible in a given language is use games. So in first order logic, the games are called Ehrenfeucht-Frese games. And they're these nice combinatorial games you play on structures. And it's a long story, I guess, but so there are two players. One player, you pick structures and you try to prove or disprove that they're isomorphic or elementarily isomorphic up to a given number of plays. And there's a duplicator and a spoiler. They take turns playing on the different structures. The spoiler wins if she can prove that in a given number of moves that the structures are not isomorphic. And the duplicator wins if he can prove that there's no isomorphism. And if you can show that a duplicator wins these sorts of games, then the thing is not expressible in the given language. So for example, use this technique to show that first order logic is very weak for graphs. In other words, you can't express connectivity of a graph. You can't, obviously there's ST connectivity. You can't even express that a graph has an even number of nodes in first order logic using these kinds of game arguments. Then when you get to monadic NP, they're slightly more sophisticated games. They're called Fagan, actually after the Ron Fagan, my colleague, Fagan games and Fagan games. And here, in addition to picking elements from the structure and you have the same sort of players, two players, but they, in addition to picking elements from the two structures in their attempt to either prove isomorphism or non-isomorphism, they also choose a coloring. So basically, monadic subsets are they're just colors that you assign to vertices. Anyway, a long story, but to prove that ST connectivity is not in monadic NP, the tool is these games. And then it's trivial to show that non-ST connectivity is expressible in monadic NP. So you can separate monadic NP from comonadic NP, but that doesn't show that because these things are both trivially in P, so it doesn't separate NP from co-NP.
Okay.
Yeah, they're both trivially in NP, the intersection of NP and co-NP. So anyway, more on that. Hopefully that explanation had some degree of sense. Okay. So our notion of inexpressibility is related to the notion of inaccessible cardinals in set theory. So loosely speaking, such cardinals are cardinals hypothesized to exist, but that we can't describe in the language of set theory using any smaller cardinals. So if we could prove the existence of such cardinals, we'd be able to actually use them to create a set model of set theory. And that would enable us to prove the consistency of ZFC within ZFC, which of course is not possible by the incompleteness theorem unless ZFC is inconsistent. So here you have these things that you can't talk about, like we can't talk about these very large numbers. Oops. But if you could actually talk about them in a precise, if you could actually point to them, then you would in fact have a consistency proof for ZFC, which is not reasonable. Okay, so in classical model theory, one studies the properties of structures, as I've described, like finite graphs that are expressible in a given language, be it first order logic, second order logic, or one of its variants like ESO or monadic NP. The limitation of the expressivity of these languages is that they don't have the ability to assign values to constants, define new functions, call these functions, or do any of sort of the looping or recursion that we're used to in contemporary programming languages. So for example, in none of these languages can you describe that a graph would be a new graph if you were to be, if you could add a vertex and some edges. Sorry for the distracting forwarding. I don't know why my charts have switched into the automatic forwarding mode. Okay, but we want to create a language where you are able to issue multiple commands where you can define constants and so on. Okay, as a simple example, if we allow the standard exponentiation operator and assume exponentiation associates from top to bottom so that these tower of exponents are as big as possible, then we can express this tower of twos using 18 bytes. Okay, I'm being very crude, not worrying about the optimal bit encoding. However, if we just define the simple function f of n, where it's 2 to the 2 to the 2 to the however many within n, then we can save a few bytes by expressing this first f of n and then f of 2. And to save space, actually, although I've used the parentheses, they're not necessary. And so that's why I get away with 13 bytes rather than 18 in this more terse expression. Okay, so we've started this investigation using two new families of languages. Okay, we start out with this very, very primitive language, PL. So it's a language having just the symbol 0, 1, plus, times, and the parentheses. So very similar to that primitive language I described before. And then we go to PLC. It adds to PL the ability to define constants, also to support the ability to issue multiple statements. And to do that, we need a statement termination symbol, which we use semicolon, just like in standard programming languages. Then from PLC, we add the ability to define functions. And from PLCF, we go to PLCF plus, which additionally gives us the ability to loop and test conditional clauses. Okay, then there's a second family of languages that we're considering based on first order logic. And this family of languages is important because it's well known that first order logic has the expressivity, the expressivity strength of SQL, the database language SQL, actually an old version of SQL without things like counting and average, what are they called? Expressions. Although if we add those expressions, then you can add a so-called counting quantifier to first order logic to get a language that's equally expressive to the new versions of SQL. Sorry, and so in analogy to the prior languages, we've been considering FOL, FOLC, in other words, adding constants to first order logic, functions to first order logic, and then the looping and so forth. And when you get to FOLCF, where you have constants, functions, looping, and conditionals, you have the full strength of so-called stored procedures that give you the full ability to program around relational databases and even store those programs in the relational databases. Okay, and we've obtained some first results regarding the expressive efficiency of PL, PLC, and PLCF. Since this is more of a philosophical talk, I'm not going to go into the details of these, but key points is that the jump from PLCF to PLCF plus, in other words, with adding looping and conditional logic is a big leap. And so you have all of a sudden, although we can quantify the expressive power of PLCF, PLCF seems way out of reach. And so to get a handle on that, we may have to go to much more fine-grained versions of between PLCF and PLCF plus. Okay. So now the deepest questions that remain, can we define expressivity within a given language, L of n, within the languages themselves? In other words, can the languages define a function f of k that gives the largest number expressible in L of k for k smaller than n? Okay, it's obviously impossible for it to define L of n, but could it express at least, can we define a function that defines the largest number expressible in L of k for smaller values of k? And why or why not? We don't know the answer to that. And then the second question, this is the conundrum question. How is it that we can talk about the smallest inexpressible number at all, even within our informal language? Can't we rearrange our words in only a finite number of ways as well, as we did in the formal language? Then when we talk about the largest expressible number, n star, what's to stop us from informally talking about n star plus 1? Okay, so that's it. Yeah, this little illustration here shows Graham's number, that crazy long number that you may have heard of, thought up by Ron Graham. I think it's actually mentioned in a paper and used for some actual purpose. But if you think of Graham's number and how amazingly big it is, there's a hell of a long way from Graham's number up to, oops, sorry about that, all the way up to Cantor and the first infinite cardinal. Okay, so thank you.
Thank you very much. We have plenty of time for questions from the audience. Please unmute yourself.
John, I have maybe a silly question. Something that first occurred to me way back in the beginning of the talk, when you were first talking about the largest definable natural number, the question of like whether or not a largest natural number actually exists. So way back in the beginning, you started off, okay, there is a largest natural number, maybe. What about that one plus one? And you said, oh, we don't think about that. But I kind of wonder when I get into these actual like philosophical arguments with people, what is a good answer to that question? What do you do with the one after that?
Yeah, it's a strange question. I wish I had a better answer for you. The funny thing is that when you do model theory, the meta language of model theory is totally informal, and it bothers me that you can talk about these things, but it seems like you run into, it's an obvious problem. I mean, if we can somehow talk about indefinable numbers loosely in our informal mathematical language, yeah, I mean, so I talk about the either the smallest inexpressible number, which immediately becomes problematic, or I talk about the biggest natural expressible number, and then what happens to that plus one? I don't know. I mean, I think the lesson is that you kind of have to stick to formal mathematics, and the rest is sort of sophistry. And I think, and that's why we reverted to studying these formal, simple language fragments and understanding their limits of expressivity. There it seems we're on terra firma and can't get in trouble. But I think that, yeah, so the minute even though it seems odd, the informal discussion doesn't work. And I can't really say much more than that.
Okay, good. So next time I'm arguing with my, my fellow grad students about why there are only finitely many natural numbers, I'll accuse them of sophistry when they don't agree with me.
Oh, well, I wouldn't say there are only finite number. Well, it's a funny thing. I mean, there are only finitely many formally expressible natural numbers. You have to throw in that we're assuming there's only a limited number of bits. Yeah, and I think that it has to bleed into this physicalist, or what did I call it? The argument has to take into consideration the fact that we're physical beings and we only have access to a finite number of bits. And yeah, essentially that there is no Platonic realism in mathematics. We're physically bound creatures, and so yeah. Anyway,
I have a question about the implications for the curriculum that we are taught. The standard curriculum in even high school, but definitely in college, is based on the orthodox view. So do you think that this will be reformed in some way, the curriculum, the usual?
Yeah, well, I don't know. I do think that, I don't know about I don't know. I think that at least in school, in before you get to the university, I guess in calculus you have limits which become problematic, of course. But for most of high school and so forth, mathematics, I don't think it's too problematic. You have induction, and as long as the induction says for any natural number instead of for all natural numbers, I don't think you get into too much of a philosophical problem. You can always push these arguments in funny ways. I mean, because often induction arguments, you say, okay, well, I can start at any k and start my induction argument, or limiting arguments, like, the first finite number of values are irrelevant, so I can start anywhere I want in these limiting arguments. But when if you start at the largest expressible number, you can't go further. So you get into a philosophical problem. I don't know. I don't know whether this is, it's just a peculiar philosophical thing. I don't know. I don't think it should reach necessarily into the high school curriculum yet, because philosophically we don't have a firm enough handle on it. I mean, this argument is something that I've been trying to develop. It's not something that I think I have perfectly refined by any means. Yeah, I mean, I would love it if other people could help me refine the argument, actually.
Also, another reason not to bring it to high school is you don't want to be accused of being a corrupter of the youth.
Yeah. Just like Cantor, right?
So, John, in practice, do you feel that you're never discovering things when you do mathematics, or?
No, I think there's the psychological feeling of discovery always. Oh, hey, Joe. I didn't know you're on. Good to see you. There's obviously that sensation, but I think that I'm also I've been inculcated in my education by this, my professors. I was at Dartmouth, by the way. I was an undergrad, and I was taught that mathematics was this Platonic thing, and I was discovering something eternal. And I believe that in a certain sense. I mean, it's certainly consistent with my psychological experience of doing mathematics, but I don't know if there were no beings to do mathematics. Would it be mathematics? I don't know. I don't know what the meaning of that is really. I mean, think about Brouwer's argument. A proof is not a proof outside of time. These steps are only understood in a sequential way. They don't mean anything otherwise. And even taking a premise and holding it with a conclusion, it takes you have to go from one to the next. And so I don't know.
A question
John,
about
maybe you
that,
can
Jonathan.
turn your screen off for the moment, okay?
Me? Okay, sure. Okay. I'm sure. Yeah. Great.
Yeah, since you mentioned Brouwer's argument, Jonathan, it seems a little bit like a failure of imagination to say that the only way you can do things sequentially is to go in time. We could certainly define linear orderings without thinking of the time as the only linear order in the world. Right, we don't have to, when we define what a proof is, we don't have to speak about time.
Well, how does this become comprehensible? I mean, I imagine you could do things in parallel, but it's still, even to understand what parallelism requires some idea of time. I don't know how we can. How do you? I mean, I realize
is time the only linear ordering? I mean, can we not say that a proof is a collection of statements together with a linear ordering with the property that each statement follows from some finite subset of the previous ones?
Yeah, but previous, I mean, isn't that?
No, previous ones means before in the linear ordering, and not every linear ordering is time.
Yeah, but I don't know how we could. I mean, if somehow you could magically get rid of time in that discussion, I don't see how you could possibly get rid of space. So it becomes, we seem essentially bound to some physicality when we do think about mathematics or express our mathematical thoughts. Seem like you don't agree necessarily.
I don't think so. I mean, I remember how we developed the theory of what proofs were when I studied logic, and in that development, there was no mention of space or time.
Oh, well, I suppose you could even say that when we talk about, informally 0.333, as I said, ... that there's maybe no notion of space or time, but I don't see how any entity could make sense of that without space or time.
Well, I agree that we as humans tend to think of things in terms of space and time, but I think it's kind of pessimistic. Well, Cantor was notoriously suffered from depression. I think that maybe if he break away a little bit more from the space-time bound, he would have been able to.
Well, Brouwer, all these guys, they suffered. I tell you, such prosecution. Cantor was ridiculed. I mean, I guess by the end of his life, he was okay, but not so ridiculed, but also Brouwer. Wow, he suffered.
So I had a question about your n star. I mean, is the is the n star in some sense inaccessible? Like, I mean, could you have an algorithm that given little n produces the n star? If you did, then you could just do that plus one, and then you would get the next largest number accessible, right? So in a way, there can't be a function that gives you the n star of little n.
There Cantor can. Well,
Can't, right? Because if there was one, right, it would produce n star, and then you could just get the next one by adding the one. It would be like a procedural way of getting that.
So the question is, for given language L of n, can you compute L of k for k smaller than n?
Hmm.
And what are the limitations on that definability? There's no question that you wouldn't be able to, within L of n, define n star for that language.
Yeah.
That's without question.
You can't access it. I mean, it is the largest one, but you can't, in some sense, you can't know what it is.
Exactly right.
It's unknowable.
Yeah. It is a strange thing. I hope that, yeah. I hope the study of this subject becomes catchy, because it seems like the questions are so irresistible, but very difficult to wrap.
Yeah, I don't think it's going to be part of the Common Core anytime soon in North Carolina. Yeah.
So John, were you at Dartmouth at the same time as Ron?
No, he's much older than me. He was there I think he's 15 years older than me. So I was there in 77 to 81. He was there, 15 years earlier.
Yeah, he was back here for his 50th reunion a couple years ago.
Oh yeah, I've just gotten to work with him in the last year or year and a half. He's so wonderful.
I agree.
Yeah.
Jonathan, what is your view of Alonzo Church's The Lambda Calculus?
Oh, I sort of like the lambda calculus as a curiosity, but beyond that, I don't know. I mean,
well, how about as a foundation of set theory of functions?
Yeah, I think it's completely equivalent to the bit foundation. Yeah, I mean, just by the Church, if we assume the Church-Turing thesis, then yeah. Well, it's not even a matter of the Church-Turing thesis. I mean, anything that can be expressed.
It's Turing complete.
Yeah, it's Turing complete. Yeah, so I could recast my whole thing in terms of function, completely in terms of functions, and using the lambda calculus. Yeah, it's a good point though. Yeah.
Can I ask, do you have an opinion on whether piano arithmetic is consistent? And would there be any profit to viewing that as a question about physical reality? Is there any experiment we can do to shed light on that question?
Oh, yeah, I don't know. I certainly imagine that piano arithmetic is consistent. I think one of the more related question that this whole line of thought may call into question is the questions like P equal NP. They may not be meaningful because we won't be, if there's not a simple proof that P equal NP or P not equal to NP. The resolution could take such large N that it becomes impossible. And moreover, because large enough N become inexpressible, at some point, the difference between P and X dissolves away. And so I don't know, I think it's quite possible that the P equal NP question just is not really meaningful. Yeah.
Okay, well, everyone, I think we should go ahead and thank John again for this wonderful talk.
Okay, thank you very much.
So this will wrap up this week. If there are people still interested in talking to John for a little bit longer and more questions, I'll leave the meeting open. Otherwise, it was good to see everyone, and we'll see you back here again next week.
So John, do you think this has any implications for people who use mathematics in the world, so-called applied math or engineers, or how should we behave differently when we promote the use of math in the world, or?
Well, I guess I don't know. I think that in the end, real numbers are not useful for, I mean, they're just obviously calculus is very useful, and everything that we've developed from the notion of real numbers it's useful. But I think that it's not in the end the right way to talk about real physical phenomena. I mean, as much as I love open sets and closed sets and point set topology, that's not what physical describes physical reality. You know, that little thought experiment I did with the cytoplasm in the cell membrane, it's just impossible. I mean, it doesn't. What does it mean for like the cytoplasm to be arbitrarily, you know, close to the cell membrane? It's crazy. I mean, it's just like sophistry, to be honest. So I think that we have to come up with some better mathematics there. I don't know quite what it is, but I think that there's sort of a delusion to think that these infinite decimal expansions are things, entities. I mean, I just don't believe that that's the case. And sure, there's a machine that we can create that will churn out digits, say, of 0.333, and maybe eventually it'll go wrong because we have flawed machines. But we just have the machine. There's no number that is really 0.3333. And if you think about numbers, we use the notion of a number in several different senses. Okay, so sometimes it's the result of a measurement, right? And sometimes it's the result of a calculation. Sometimes it's just a matter of definition. So pi is sort of a definition, and we can switch from the definition or the conceptual definition of what pi means to computing its digits, but it's two different senses of the number. And I don't think that these things exist in their infinite expansion. There's the machine that we can define to compute those digits, but the infinitude of digits, I don't know. I mean, why should such a thing exist?
So Jonathan, why do you, if you want to have mathematics to model the universe, what do you propose to model quantum mechanics?
Okay, that's actually a couple of slides that I left out. Okay, so there's a pretty prominent finitist, a physicist named Nicolas Guissin, and he proposes that we think about real numbers as these probabilistic things where we churn out bits, probabilistic bits. You know, there's kind of like qubits, not quite, and so the result. I mean, this isn't quite answering your question, but I think it's a step in the right direction. So instead of thinking of a real number as a completed entity, we think of it, if it's the result of a measurement or even a calculation, we generate these digits sequentially with some probability. And as we get further along, they become increasingly unsure. And so the probability converges to 0.5, has become uniformly uncertain. And sort of a nice description of what a real number might be from a probabilistic viewpoint. And I suggest you read his work. The question I have with this formulation, however, is that we're describing real numbers probabilistically, but how do we even describe these probabilities if we don't yet have a notion of a real number? So it may run into some circularity problems. Now, so yeah, actually your original question is how do I, if quantum computing is the ultimate model of reality, then I have to, my argument was that we should replace the foundations of mathematics with the notion of a bit and computable mathematics rather than the notion of a set. Does that push us then to have to replace the fundamental notion and the building block of mathematics, the qubit? And that becomes problematic just because of this sort of circularity concern that I have with Gissin's formulation of real numbers. But yeah, again, my head is exploding just trying to I don't know. I mean, from the simple you get, it becomes quite complicated. Yeah, I don't know.
So have people tried to do real analysis with just sort of saying there's only really countably many real numbers because a real number is the Turing machine that produces the digits. Has anyone sort of taken that view and tried to derive the consequences of that? I imagine, showing X is bigger than Y is good, showing X is less than Y, but showing X equals Y, that's tricky, right?
Yeah. Actually,
because the machines have to agree forever, right?
Yeah, I don't know. Daron, do you have any idea?
Has anybody done that sort of thing?
I don't know. Yeah. I mean, Daron has thought about discrete. His famous thing is that he talks about how differential equations are just the degenerate form of a finite difference equation, and actually, the calculus was developed completely intuitively by Leibniz and Newton. I mean, the epsilon delta formulation of calculus only came like 150 years later. And so it shows that calculus somehow works out without the formalism that we've come to use. But anyway, Daron, do you know more about this? It's actually, I'm sort of quoting you.
I think Dr. Z's been having some trouble getting his microphone to work. Maybe he's typing something in the chat, though.
Okay.
I can partly answer your question. There's quite a bit of work on what are called constructible real numbers.
I've heard that.
Of which there are only countably many, but it hasn't really taken off. I mean, there are a lot of different logics. There are different systems. My own former advisor, Abraham Robinson, of course, tried to turn the world upside down with the non-standard numbers. But it seems that the real numbers as we currently understand them in the context of ZSC are quite useful and by now rather well ingrained into our consciousness. And this is why, as you were saying before, Jonathan, new ideas in mathematics are introduced, but they're usually on top of real numbers. We don't seem to be very close to being able to abandon them in favor of something else, just to build other things on top of them.
Yeah, I think though that some of the deepest problems in physics may have something to do with the fact that we haven't quite hit upon the right mathematics. We're trying to reconcile quantum mechanics with gravity. The real numbers seem great for gravity, but something's wrong when you think about them, quantum mechanically. So maybe we just maybe we have the wrong mathematical formalism, and that's preventing us from really seeing how these two theories converge. Although, I'm sort of speaking over my head because I'm not a physicist.
So maybe we'll have time for one more question for John, if anyone has anything. Any closing thoughts?
There's an NYU philosopher named Tim Maudlin. You familiar with this name, Jonathan? Who has built up a whole new mathematics, basically from its topological roots, in order to better describe physics. I found his work quite fascinating, and you might enjoy it as well. It's
sounds great. Yeah.
Maudlin.
Oh, neat. I'll look into that. Yeah, actually, it was I think a discussion I had a long time ago with Brian Greene that got me thinking about this. And he, in one of his books, he talks about how he's basically said exactly what I said, that his feeling about the problem with the unification of gravity and quantum mechanics had to do with a failure of our mathematical imagination. So, okay, well, thanks a lot for the suggestion. I will look at Maudlin's work. And thanks everybody for coming and the interesting questions.
Yeah. Thank you.
Cliff, Al, Daron,
Hi,
Joe,
Peter. Good to see you.
Jonathan, everybody. Great to see you all.
Okay, bye.
Bye-bye.
All right, bye everyone.
Bye.